Let's look at a couple of sample problems out of 5.3 and see how to work the binomial probability distribution problems. So the first problem out of 5.3, they tell us that x is a binomial random variable, and they give us an n value, an x value, a p value, and they ask us to calculate what the probability is. So remember that the probability function for binomial probability distribution is n choose x times p to the x q to the n minus x, where p is the probability of success, q is the probability of failure. So when we say probability of success, we mean the probability of x occurring, whatever x stands for. If we're flipping a coin, let's say we're flipping a coin and we're counting how many times we see heads, x would be the number of heads. If we're flipping a coin and we're counting how many tails there are, we will let x be the number of tails. So the probability of success for the first situation would be the probability of getting a heads, which if there are two sides, there's one heads. On the second case, the probability of success would be the probability of getting tails, two sides, one tails. Now in this case, they're the same, but I just want to illustrate whatever our random variable is called, having that occur, that's what we mean as success. Now, keep in mind, success is not always a desirable thing when we're looking for binomial probabilities. If x is the number of people that catch the flu, it might be that the probability of a person catching the flu is 30%. Now, it's not desirable that a person catches the flu, but if what we're counting is how many people catch the flu, then the probability of that occurring, that's what we consider success. So P is just the likelihood of X occurring, of our random variable happening. In a binomial probability distribution, we have two options, success or failure, so P plus Q has to add up to 100% or 1. This T out front, just as a reminder, that just tells us how many different ways are there of having X successes and then the rest failures. One example from the book is, and I think I put this in the PowerPoint, you have a quiz, you don't know anything about the questions, and they're multiple choice. Each of them has A, B, and C, and you're randomly guessing. So, assuming there's only one right answer for each question, for each question you have a 1 out of 3 chance of getting the question right. So for each question, probability of getting it right is 1 out of 3. Probability of getting it wrong is 2 out of 3. So if we want to know, so let's let X be the number of correct responses. Basically, how many questions did we get right? Let's think about what's the probability of x being 1. That means, what's the probability of getting one correct answer? The piece out front, that takes the probability of getting one correct answer and it multiplies it to how many different ways are there of getting one correct answer. So in our case, if we're wanting to find the probability of x equal 1, we have 1, 2, 3, 4 trials, and we're looking for the probability that x equals 1. That means that out of the 4 trials, we get one correct. So when we do n choose x for this situation, 4 trials, x is 1. So this is telling us how many ways are there of getting one correct. Well, let's just talk through that. We could get the first one right, and then the next 3 wrong. We could get the first one wrong, the next one right, and then the next 2 wrong. We could get the first 2 wrong and the last one wrong. We could get the first 3 wrong and the last one right. So there are 1, 2, 3, 4 ways of getting exactly one right or correct answer. That's what this piece calculates for us. The number of combinations of getting exactly one correct answer. If this was a different number, that would be the number of ways of getting that number of successes. The other part, the p to the x, q to the n minus x, that's the probability of one of those. The probability of one of those things happening. So the first one that we listed was the first one correct, the other 3 wrong. So for that to happen, that's the probability of getting the first one right, and the second one wrong, and the third one wrong, and the fourth one wrong. Excuse me. Since they're independent events, that's the probability of getting the first one right times the probability of getting one wrong times the probability of getting the third one wrong times the probability of getting the fourth one wrong. So 1 success, 3 failures. If the probability of success is 1/3, that's 1/3 to the first. Probability of failure is 2/3. If there are 4 trials and we're looking for 1 success, 2/3 to the third power. Notice 1, 2, 3. So that portion of our probability function, that just calculates for one way of having exactly 1 success. What is the probability of that occurring? We would then take that probability times there are 4 different ways of getting that occurrence. So if we multiply this probability of one of those occurring, that's 2 times 2 times 2, so 8 over 3 times 3 times 3 times 3, 8 over 81. So basically 8 over 81 is the probability of getting the first one correct, the other 3 wrong. Well, that would be the same probability for getting the second one right, the same probability for getting the third one right, the same probability for getting the fourth one right. So we take that probability, multiply it by how many different ways there are of getting exactly one correct, and that'll give us the total probability for how likely is it of getting exactly one correct. So again, the first piece tells us how many different ways there are of having this number of successes. This portion calculates what's the probability of one of those events happening. So that accounts for lots of different ways of it happening. So let's go back to our problem. So we have a binomial probability experiment where there are 4 trials. The probability of success is 0.45, which means the probability of failure to be the complement of that, so 0.55. We want to find the probability that x is 0. So to begin with, let's write out our probability function. That's n, choose x, over p to the x, q to the n minus x. So that's 4, choose 0, 0.45 to the 0 times 0.55 to the 4. So to calculate this piece out front, we take the top number factorial divided by the bottom number factorial times the difference in these numbers, the difference in those, factorial. And then anything to the 0 power is 1. And then we still have our 0.55 to the 4. Close that out. So 4 factorial, that means 4 times 3 times 2 times 1. 0 factorial, by definition, is 1. 4 minus 0, that's 4 factorial, so 4 times 3 times 2 times 1 times 1 times 0.55 to the 4th. We'll notice we have some common factors that we can cancel out. All those cancel, that leaves us 1 times 1 times 0.55 to the 4th. We take our calculator out and do 0.55 raised to the 4th power, 0.0915. I think it asked around to 3 decimal places, so 0.092. 0.092. So that's part A. So let's look at another one. Let's look at number 3. Let me blow this up so we can copy all of it. Number 3 says, as a quality control inspector for toy trucks, you observe that 6% of the time the wooden wheels are bored off-center. If 6 wooden wheels are used on each toy truck produced, what is the probability that a randomly selected toy truck has no off-center wheels? So, first of all, let's define our random variable. Let's let x be the number off-centered wheels. So if we're counting off-centered wheels, then our probability of success, that's if we look at a single wheel, what's the probability of finding that wheel to be off-centered? That's not saying it's desirable for the hole to be off-centered, but if we're counting off-centered wheels or off-centered holes, our success is if in a single trial, what is the probability of on that trial having an off-centered hole? And it says that 6% of the time, 0.06, the hole is drilled or found to be drilled off-center. So 6% of the holes are off-center, and the complement of that, 94% or 0.94, that's how many holes are drilled not off-center or that are centered. If a single toy has 6 wheels, if we look at each wheel, then we're doing 6 trials. We look at a wheel, we see, is it centered or not centered? We look at another wheel, is it centered? Is the hole centered or not? Another wheel, is it centered or not? We do that 6 times, one for each wheel, because there are 6 wheels. So each wheel is independent of each other. It's either off-centered or not. So we have outcomes. The probability of finding it off-centered is 6% for each individual wheel. So we have repeated trials, success or failure. They're repeated trials, so this is binomial. So the probability is n, choose x, p to the x, q to the n minus x. So that's our probability function. If we want to find the probability that there are no off-centered wheels, that's the probability that x equals 0. So we replace x with a 0. So 6, choose 0. 0.06 to the 0 power. 0.94 to the 6 minus 0. Now let's come over on the side and calculate 6, choose 0. Before we calculate that, let's think about this. If we have 6 wheels and we're looking for are they centered or not, if we want to have 0 off-centered wheels, if we're looking for the likelihood of finding 0 off-centered wheels, then there's only one way that can happen. That's if the first one has a centered hole, the second one, the third one, fourth, fifth, and sixth. The only way we can have no off-centered holes is if they're all centered. If even one of those is off-centered, not centered, then they're not all centered. So there's only one way that could occur. Let's make sure that this permutation gives us exactly one way of that happening. So 6 factorial, or is that a combination? Anyway, 6 factorial over 0 factorial times their difference, 6 minus 0 factorial. 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1. Notice this is the same factorial, so all of those similar factors cancel. 0 factorial is also 1. So 1 over 1, yes, that's 1. So this is 1. That means there's one way of getting 0 off-centered holes. Times 0.06 to the 0, anything to the 0 power is 1, times 0.94 to the 6. So 1 times 1 times 0.94 raised to the 6th power. To 3 decimal places, this would round up. So 0, carry your 1, so 0.690. You could think 689 rounds up to 690. That 8 rounds that up to the next. So 0.6, that's not a 6, 0.690. So that's how likely it is that all 6 wheels have a perfectly centered axle hole drilled if the likelihood of just one of them being off-centered is 6%. All right, let's do another. Number 4. Of all the trees planted by a landscaping firm, 30% survive. What is the probability that 13 or more of the 15 trees that just planted survive? So let's let X be the number of trees that survive. So we're looking at each tree, looking, does it survive, does it not survive? So if we're counting how many trees survive, then success is surviving. We're counting the trees that survive, so that's what's successful, surviving. 30% survive, so the probability of success is 30%, 0.3. The probability of failure is 70%, 1 minus 0.3, so 0.7. So if 30% survive, then 70% don't survive. Which, by the way, I'm probably not going to buy trees from here. There's only 30% chance that one of those trees, each tree survives. That's probably not really good. So we want to find what's the probability that 13 or more of those trees survive. So 15 are planted, so N is 15. So we're looking for the probability that our random variable is equal to 13 or greater than 13. 13 or more, so that's greater than or equal to 13. Well, if we have 15 trials, that means that the probability of X being 13 or X being 14 or X being 15. Since these are independent events and they're mutually exclusive, if we have exactly 13 surviving trees, then we don't have exactly 14. If we have 13 or 14, we don't have exactly 15. X being 13 plus the probability of X being 14 plus the probability of X being 15. So if we had to do this calculation by hand, that would take a little while because we would have to take our probability function. For this situation, N is 15. P is 0.3, Q is 0.7. So we have to take our binomial probability function, calculate it for 13, then calculate it for 14, then for 15, and add those together. Now, fortunately, for certain p-values and certain n-values, there's a table in the book that gives those calculations. Starting on page 713, we have several binomial probability tables. They start for n equaling 2, so they're for 2 trials, 3 trials, 4 trials, 5 trials, and then we have several different p-values. So if you have a p-value of 0.01, so that's 1%, 5%, 10%, 20, 30, 40, 50, if you have any of these p-values across the top and any of the n-values listed down the side, we have n values, let's see, at least up to 15. You have n values at least up to 15, and any of these p-values, we can use the table. So notice on ours, we have an n of 15, a p of 0.3. So if we go to our table, a p of 0.3, that's this column. N of 15, that's all of these. So all of these values. Double check, make sure I followed. Actually, I was on the wrong column. It's this column. So any of these values in this column apply to 15 trials, P being 0.3. So this first one, that's for x being 0. This is for x being 1, x being 2, x being 3, 4, 5, 6, 7. So we have x being 13. So the probability of x being 13 when n is 15 and p is 0.3. So again, let me double check. The p of 0.3 column, that's this column. So this column where x is 13, we get basically 0. Where x is 14, we get basically 0. When x is 15, we get basically 0. So basically, if there's only a 30% chance of survival, there's almost no chance of getting 13, 14, or 15 trees survive. Now notice in the table, it said 0 plus. If we went out beyond 3 decimal places, then there would be a slight possibility of that occurring. It would be pretty slight. So notice they even give to 4 decimal places. Our table only went to 3 decimal places, but even to 4 decimal places, there's basically no chance of that occurring. Now let's take the same question. Let's copy most of this information over. And let's calculate another probability. Let's calculate the probability, we don't need those, of having 5 or more survive. So if there's only a 30% survival rate for each tree, and we have 15 trees, what's the probability of having at least 5 survive? So that's the probability of X being 5 or 6 or 7 all the way up to X being 15. And we could get each of those probabilities, one for 5, one for 6, one for 7, one for 8, all the way up to 15, and we could add those up. Notice the ones we're leaving out are 0, 1, 2, 3, and 4. Also, we know that if we add all of the probabilities from 0 up to 15, that takes care of every possible situation. So if we add all of those up from X being 1 all the way to 15, that has to add up to 1. Notice if we do from 5 all the way up to 15, that's like 11, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, so that's 11 different probabilities. Notice that leaves 1, 2, 3, 4, 5. So we could either calculate all 11 of those, or in our case, use the table to get all 11 of those. Well, there's only 5 that are remaining. We could get this probability, the probability of X being less than 5, so 0, 1, 2, 3, and 4. This probability that we're looking for is the complement. It's everything that's left after we calculate this probability. So the probability of X being less than 5, let's see, if we go to our table, the probability of X being 0 is 0.05, 005. The probability of having one tree survive, that's 0.031. The probability of having 2 trees survive, 0.092. 3 trees survive, 0.170. And 4 trees survive, 0.219. So if we add those up, 0.005 plus 0.031, if we add those together, we get 0.517. And keep in mind, those are all rounded to 3 decimal places. So the probability of having fewer than 5 is 0.517. So the probability of having 5 or more, that's the complement. That's everything else. So 1 minus 0.517, or 0.483. Now this wasn't a huge deal since we had a table. We could have just taken the values from 5 on down, added those up, or we could say 5 on up, 5 up to 15, added those together. But think about if we had to do each one of those by hand, would you rather do 11 or do 1, 2, 3, 4, do 5? So we could figure out each of those 5 probabilities. We're wanting the complement, so 1 minus what we found here. So either way is fine, but often the complement in many cases will give you a shorter calculation to do. So just keep that in mind as you're calculating these.